Hello, welcome back. In this lecture, we'll discuss delay time estimation of a mass transistor. To know the delay time, what we need to know is we need to know the value of resistance that is offered by a mass layer and the capacitance that it will involve in. So RC both together will give you the delay. So the first and foremost thing that you need to understand is sheet resistance concept. The sheet resistance means every material like aluminum, copper, gold, silver, whatever that we use for interconnection or anything, every material will have a resistivity which is represented by the term by the letter rho. So rho is resistivity of a material. Now the sheet resistance concept is the square material which is in square shape having L is equal to W. This is width of the layer and this is length of the layer with a thickness T. Then it offers a resistance RAB, that is resistance between the terminals A and B. Between these two ends, the resistance offered by this plate is RAB is equal to rho L by A. A is area of the plate. A is length into width. Rho L by A. R is equal to rho L by A, which you know. A is W into, sorry, not it is length into width, it is width into thickness. Two dimensions. Width into thickness. Now substitute this R is equal to rho L by WT. For any material which is in square shape, we will be having L is equal to W. If the L is equal to W, then it will become R is equal to rho by T per square, because this is square. As this is square, we have made it equal and both got cancelled. So it became rho by T. So that's why we need to mention RAB is equal to rho by T ohm per square RS, where RS is independent of the area. That means if you take 1 centimeter by 1 centimeter piece, that offers the same resistance which is offered by a 1 meter by 1 meter sheet also. So offer also. So and it is dependent on the resistance value changes. Now it does not change by changing the size of the sheet in square form, but it changes if you change the thickness of the sheet. So that is what is mentioned here. RS is independent of the area, dependent on the thickness of the layer. And obviously if you change the material, then resistivity changes, then R changes. For diffusion regions, thickness gives you depth of the region. Resistivity can be altered. Thickness can be altered by depth of the region, and resistivity can be altered by the doping concentration. If you dope it a highly doped material will have less resistance. Low profile doping gives you large resistance. Now sheet resistance of different conductors is given in this table. If it is a metal, the sheet resistance will be minimum of 0.03 ohms and typically 0.07 ohms, and it is for 1.2 micrometer technology it is 0.1 ohm. This is how sheet resistance of metal changes. Whereas metal offers least resistance, as we all know, because it is a conductor, whereas diffusion offers large resistance of up to 100 ohms, 25 ohms and 10 ohms. Silicides offer 2, 3, 6 almost equal to. Silicide is nothing. This silicide offers low resistance, which almost act as a conductor. Polysilicon used for fabrication of small value of resistances and used to have connected the gate terminal to silicon dioxide dielectric layers. Now, with all these inputs, if you estimate the n transistor channel resistance, it is of 10 kilo ohms. Resistance is 10 kilo ohms. P transistor, P channel transistor channel, P channel transistors channel gives you a resistance of 25 kilo ohms. This is resistance. And coming to the concept of the sheet resistance, when a basic feature size, which is 2 lambda by 2 lambda size channel length, is a square. Now that one square resistance gives you 10 power 4, 10 kilo ohms of resistance, whose L is equal to W, Z is equal to 1. If Z is equal to 1, it is offering 10 kilo ohms. If Z is equal to 4, it will offer 40 kilo ohms of resistance. That is how we have to calculate. Now we understood what is resistance. Now let us estimate. Let us try to understand what is area capacitance of different layers. We have just now we have finished area resistance of different layers. Now we are trying to understand area capacitance of different layers. The area capacitance formula for capacitance is C is equal to epsilon A by D, where epsilon is epsilon naught and epsilon INS. Epsilon naught is the free space permittivity and epsilon INS is the insulator that is used, permittivity of the insulator. D is thickness of SiO2, A is area of plates, and epsilon naught have a standard value 8.854 into 10 power minus 14 farads per centimeter, which is the permittivity of free space. Where if you use SiO2 or something as a permittivity, whose permittivity is almost equal to 4, it is 3.8. So now the capacitance offered by different layers in different technologies. It is 5 micrometer technology, 2 micrometer technology, 1.2 micrometer technology. So each node, each technology nodes have a different value of capacitance. Now we understood what is the capacitance that is offered by each layer, different layers, metal to substrate, metal 2 to substrate, polysilicon to substrate, diffusion, channel capacitance, all these. We need to understand the standard of square capacitance. This is not for square capacitance. We are trying to know what is square capacitance and how it is evaluated. After square capacitance, we can go for delay calculation. Now this standard unit of capacitance is minimum feature size, that is 2 lambda by 2 lambda device will be having 1 square Cg. This should be printed here, but it is PPT changed. This is 1 square Cg. This is square Cg. 1 square minimum feature size is 1 square. This should be read as square. This box is 1 square Cg. Gate to channel capacitance for L is equal to W. For example, if this is a 5 micrometer technology, L into W will be 5 micrometer into 5 micrometer, which is 25 micrometer square. The capacitance value is 4 into 10 power minus 4 picofarads. This is 4. All these are picofarad, values in picofarad. So gate to channel is 4 into 10 power minus 4. So 4 into 10 power minus 4. Now convert it to the square. We have got the area into capacitance gives you the gate Cg of this technology gives like this. This is how we calculate for every dimension. We can calculate by considering the dimensions of different layers. We can calculate the capacitances. Now once having the capacitance value and resistance value in hand, what we can estimate is the delay time. The delay time tau is RC. Tau is equal to RC. 1 RS and 1 CG gives you delay time. As we have just calculated for 5 micrometer technology as an example, for 5 micrometer technology, 1 RS is equal to 10 power 4 ohms, which is 10 kilo ohms. And this Cg just now we have seen 0.01 picofarads. Now this delay offered by a 5 micrometer technology with minimum feature size transistor. That is, minimum feature size means 2 lambda by 2 lambda, L is equal to W. So minimum 2 lambda by 2 lambda device of minimum feature size of 5 micrometer technology introduces 0.1 nanoseconds, which is very small, 0.1 nanoseconds of time as delay. You can see here input is changed at time 0. Let us say input is changed from 0 to 1. That is passed through next transistor after a delay of 0.1 nanoseconds, which is 0 to 1 has been made at 0.63. This is 63% of the complete output. For the time taken to make the output high is the delay. This is represented as a lumped parameter as square Cg. This is how capacitance delays are estimated, including the parasitic capacitances 0.2 seconds and this 0.3 nanoseconds. This is 0.1 nanoseconds, and including the parasitic capacitances, the overall delay comes as 0.13 micrometer for a 5 micrometer technology. I think you understood. Thank you for watching. Thank you.